All right, so for the X bar, the sample mean for A, you add these up, you got 210 divided by 635. And then the range would be the highest minus the lowest, so 40 minus 30, 10. And then the other one, you add these up, you got 210. So X bar, the average mean, the sample mean, sorry, for B is 210 divided by 635. And then your range here is going to be the highest 70 minus the lowest 10. So you guys got 60 for that. This should be an equals. All right, so is that what you guys got? Range of 10 and range of 60? And both had a mean of 35. Cool. So then, they both have a lifespan of 35 months. So they will both last you, on average, 35 months. This one has a range of 10 months, so it could break anywhere from 30 to 40. This one has a range of 60 months. So in other words, it could last you as long as 70 or only as long as 10. Has a bigger range of the possibilities of how long it lasts you. Which one would you rather buy and why? Talk to your neighbors for 30 seconds. Go. There's no wrong or right answer. Just come to it. All right, so who would prefer model A? Okay, let me give me a reason why. Anyone? Yeah?
It's consistent.
It's more consistent? Okay. Who would prefer model B? Yep. Why?
Because it has potential to last longer.
Okay. So it's potential.
Stats, bro.
Right, so you're kind of willing to gamble a little bit, right? Gamble. So yeah, so it's just kind of, up to your personal preference, right? Good deal. But you can definitely see, like, these are definitely more consistent, for sure, right? Smaller variance. These ones, more variance in there. Could do really poorly or could do really, really well. How about Rizzo? Go ahead.
There are better ways to measure variation besides range. Range equals the maximum value minus the minimum value. It is very sensitive to extreme values, therefore it is not
As useful?
as useful as other measures of variation. One better way that we will use a great deal is variance. First, let's look at different ways to compare the averaging.
Great. So, range, not a bad way, but there's much better ways. Variance. That's the one that most of us use. So, what's the mean of these 5 test scores? I add them up, divide by 5, because there's 5 of them. I get an average score of 80. Good? Another way that 5 tests can average to 80 is if they're all 80. Right, so let's kind of look at that target of 80s. So I'm going to take each test score and see how far it is from the average. So here's 75, is 5 below the average. Right, that's my first test score. The next one, 80, is right on the average. My next test score, 83, is 3 above. My next one, 77, is 3 below. And then my last one, 85, is 5 above. If I add up all those differences, I better get 0. Because the average difference from the mean should be 0, right? That's the whole idea. Otherwise, 80 wouldn't be my average. Right? That's kind of the idea. So here's the problem. I can't just add those up. So what someone said was, well, why don't we square them all so then they're all positive? So when we add them up, they won't equal 0. So when you square a negative number, it becomes positive. Yes?
Yeah, but when you square a number with the slightly bigger than another one, the differences are magnified. Why don't you take the absolute value, then you get the best.
That's another possibility. So some people do what they call, that's called a mean average distribution. and that's another thing, but people more often use the standard deviation. So we will take a look at this. We're gonna focus on that one because you're right. That's another possibility. So we'll kind of go through this. I understand what you're saying. What he's saying is, well, always take the actual value of them and just add them up then. And that is totally a valid thing, and that is something that people calculate also. Totally. I don't know, standard deviation has all these really cool, nifty properties that are useful in other ways. So we're going to kind of take a look at it. So first, variance does this. It takes all the amounts above and below, all the differences, right? So -5, 0, +3, -3, and 5, and squares them all. So if you square them all, you'll get 25, 0, 9, 9, and 25. Everybody on board with me? I just squared them all. And then I average those. I add them up, divide by how many there are. Good? And that's my variance. So you square all the differences, and then you average them. You add them up and divide by how many there are. Here's the problem. Like Sterling was saying, we're taking the average of squared differences. So at some point, maybe, Carl, we should undo the squares. How do you undo a square? Square rooted. So the standard deviation, which is what we deal with more often, is the square root of the variance. And that's it right here. Standard deviation, oops, why is it giving me issues? Square root of the variance. Here are the formulas for it. Right, the population variance, that's called sigma squared. It's the lowercase sigma. This guy is the uppercase sigma. This is the lowercase sigma, circle with a little tail. Circle tail. Circle tail. Sigma. Sigma. This is the uppercase. This is the lowercase. Right, just like an A and an A, right? An A and an A are different, uppercase, lowercase. Same sort of idea. Okay. So this is, the population variance is sigma squared. The standard deviation is sigma. These are the formulas for it, right? You take every x value, subtract off the mean, and then you square those values, and then you average them. You add them up, divide by how many there are. If you square with that, then you get the standard deviation. You'll notice that that the population variance is the square of the standard deviation, right? If you have the standard deviation and you want the variance, you just would square it. So in other words, if this was 3, that would be 9. Everybody on board with that? So that's why this is sigma, and that's sigma squared. It's just the square of whatever this is. Likewise, this is the square root of whatever that is. If that was 9, this would be the square root of that. This would be 3. So since that's sigma squared, this is the square root of sigma squared. So whatever that is, you take the square root of it. And that's how you get to there. Which is why this is called sigma squared, this is called sigma. Right, because this is the square of this one. Everybody, does that make sense for folks? Okay. No? You want to talk to your neighbors about it for a second?
No.
Yes, no? Yeah, talk to your neighbors about it for 30 seconds. Go ahead. Yes, kind of. I'll show you an example in a minute. So why don't I show you guys an example? Maybe that'll make things clearer. All right. So first of all, are these things statistics or parameters? Guys, statistics or parameters? Parameters. Why? It's for the population. Everybody on board? Did everybody get that last part?
Yes.
Okay. They're parameters. All right, eyes up here, guys. Here is an example. My family, usually we don't have the whole population. But my family, there's only 5 of us. The whole population of my family is 5. Everybody got that? 5 people. So here's my family. So my sister is 57 inches. My other sister, 58 inches. My mom was 62 inches. I'm 63 inches. My dad's 65 inches. If you average our heights, it's 61 inches. Our population mean, mu, 61 inches. Good? Now I'm going to find the variance. I'm going to figure out how far every person is from the mean. My sister, she's 4 below the mean, -4. My other sister, 3 below the mean, -3. My mom was 1 above the mean. I'm 2 above the mean. My dad is 4 above the mean. Then we're going to square all those numbers. Square -4, square, that's 16, square -3, 9, square 1, square 2, and square 4. And then average them. Add them up, divide by 5, because there's 5 of us. So our variance is 9.2 inches squared. Now remember, standard deviation, we like that better because for a couple reasons. Let's take a look. It's the square root of the variance. It's also often more useful because it's the same units as the data is in. Right? So if my variance is this, the square root of that would be 3.0 inches, just regular inches. The standard deviation, I'm going to say this one time, because all you guys are going to ask me questions later, it's the general idea of a standard deviation is that it is, on average, kind of typically how far every data values are from the mean. So on average, how far are the data values away from the mean? About a standard deviation. On average. Some are going to be more, some are going to be less. But it's kind of a general sense of about, roughly, right? So I would say here that my family is 61 inches, give or take 3 inches. That's kind of what I would say to people. Oh, we're 61 inches, give or take 3 inches. Right? Which is, we're 61 inches, give or take this much. If I said 61 inches, give or take 10 inches, then that means we'd have a much bigger variance, right? Our heights would be like wildly different. But we're all Asian, so we're all pretty short. So why is variance important? It tells you kind of the idea of the spread of the data and how consistent a variable is. So here, this one, very consistent, right? No spread at all. This one, a pretty big spread and not that consistent. Right? It's pretty different from each other. So that's kind of why we need the variance, to kind of look at how much the data, how consistent it is, and what the spread is. All right, so let's get a good reader for this one. Eduardo?
Almost all of what we will do in this class involves samples of data. If we are trying to estimate the variance or standard deviation of a population from a sample only, it is often too small due to the fact that we are only using the sample versus the population. To adjust, we divide by n minus 1 instead of n. This is what we call the sample variance and sample standard deviation.
Right. So often, right, we take a sample, our data's going to be off a little bit, our mean's off a little bit, everything's off a little bit. So sometimes our standard deviation will be a little bit too small. To give ourselves a little more room for error, instead of dividing by n when we average, usually you add things up, divide by n, we're going to divide by n minus 1 to make it a little bit larger. Say I have 20 bucks, and I divide it amongst these 5 people. How much do they each get? $4? Right? But what if I divide by n minus 1 of them? If I divide by 4 of them, now how much do they each get? $5, a little bit more. So when you divide by a smaller number, you have less people to split it up amongst. Everybody gets a little bit more. So dividing by n minus 1 makes it a little bit bigger. Someone from my morning class pointed out that, well, what happens if your sample is really big? It should be pretty close to the mean then, right? And yeah, that's true. the beauty of it is, as n gets really big, like say n was 1,000, if you add all up 1,000 things, if you divide by 1,000 versus dividing by 1,001, it makes almost no difference at all. But dividing by, if my sample size is small, like 5, the difference in dividing by 5 and dividing by 4 is kind of large, because my sample size of 5 is kind of sketchy, right? So that's the kind of nice thing, is that as your n gets really big, dividing by n minus 1 doesn't really matter that much. It's almost the same as dividing by n. All right, so in light of that, here's are our formulas. So on your notes, right? The first one you already entered above. You said for populations, right? Variance and standard deviation and theoretical formulas is this one here, and the bottom one is for samples. Right? Because now we're talking about samples. These are the formulas, and you'll notice that the differences are, instead of being sigma squared and sigma, it's s squared and s. Sigma are the Greek letters. Whenever we're talking about populations, we use Greek letters. Whenever we're talking about samples, we're using these regular, ordinary letters, regular letters. So sigma is the Greek s. So here, for the sample, we just use regular s. Regular s squared and regular s. The other thing you'll notice is that instead of having mu, our population mean, we're using x bar, our sample mean. And the last thing, like I said, is we're using n minus 1 instead of n. We're going to add in another little formula here later on at the end of class into this spot here, so just know we're going to come back to that in a little bit. All right, did that clear up people's questions about that? A little bit? All right, so I'm going to do an example with you. So flip the next page. Top of the next page. Oh no, just flip the page over. Oh no, wait, I'm sorry. Yes, flip the next page. My bad. Yes. Find the variance and standard deviation for the sample of how long TVs lasted. So again, these 6 TVs, those are not all the TVs of that's not all the Model X37s that were made. It's just a sampling of all the X37s that were made, right? So this is a sample. Everybody agree with me? Do you guys understand what I'm saying? There's only 6 TVs. They made more than 6 of these. This is not the whole population. This is just a sample of 6 of them. Okay. What was my X bar again? Anyone?
For Model A, 35.
Yep, X bar was 35. So I need to figure out how far each of them is from 35. So again, remember, I'll write out for you my formula up here. My s squared is going to equal the sum of my x minus x bars squared divided by n minus 1. So we're going to do the first part first, x minus x bar. X minus, so leave yourself, we got to put 2 lines in here, so write kind of small. We're going to try to fit 2 lines of information in here. So x minus x bar, how far is this from 30 from 35? It's 5 below, right? Or you could just put 5 because we're going to square them all. You can do, if you want to just leave them all positive, it's fine, because once we square them all, they're all going to become positive, so it doesn't really matter. How far is 35 from 35?
It's the same.
0. Yep. 40 from 35? 5. 35 from 35? 0. 30 from 35? Minus 5. And 40 from 35? Yeah, plus 5. Now, our next step is to square them all. So I'm going to square them all. X minus x bar squared. So squaring negative 5 gives me positive 25. Squaring 0 gives me 0. Squaring 5 is positive 25. 0, positive 25, and positive 25. Okay, so far? Now it's the last step. Kind of average them. Add them up, divide by n minus 1. So I'm going to add them up and divide by n minus 1. That's going to be my s squared. So add them up, divide by n minus 1. What's n? N is, what's my n?
6.
6, so divide by 6 minus 1. Why is n 6? Because there's 6 of them. 1, 2, 3, 4, 5, 6. So if I add up these, I get 100. And 6 minus 1 is 5. So that means that my s squared is 100 over 5, 20. And then my s, my sample standard deviation, is the square root of 20. So I think it's like 4.5 maybe? 4.5? 4.5. All right. Everybody all right with that? You guys do the other one. You have homework due on Tuesday.
Oh, on Tuesday too?
Yeah.
No, just Tuesday. We don't have
All right. So here,
Yeah, bro. Big bad.
we find out how far each one is from the mean, right? Negative 15, 15, 5, 35, negative 25, and 15, negative 15. You can make them positive. It doesn't really matter because you're going to square them all anyways. And then we're going to square them all, and then we're going to add them up and divide by, kind of average them. Add them up and divide by n minus 1. So it's kind of like an average but warped a little bit. So add them all up and divide by 6 minus 1. So what do you guys end up getting when you do that?
220 or 2,515.5.
Yeah, so you end up with an s squared of 510
We
and an s of square root of that.
22.
So s squared 510, s is equal to square root of 510, which is, what do you guys get? What was it? 22.6. So yeah, definitely a much higher variance than 4.5, which was the other TV. All right, so this lab problem, we're going to skip that one since we just did one that was similar, so just write skip there, that's fine. Just that one problem. Skip that one. And variance, all right, so the notation again. Sample standard deviation, that's S. Sample variance, S squared. Those have those relationships, right? This one, sample variance is the square of sample standard deviation. That's why it's S squared. Sample standard deviation is the square root of sample variance. That's why if this is S squared, square root of S squared is S. Population standard deviation, Greek letter, sigma, right? Circle with the tail. Population variance, sigma squared. So this is at the bottom of your next page, or the bottom of that page, I guess. And then I want you guys to take a couple minutes and sort out what goes in the rest of those spots. Just. All right, so let's go over these guys real quick so we can get out of here on time. So first of all, the first one, someone read it. Let's read it. Let's see.
Denotes the sum.
Denotes the sum of a set of values. What's, that's, yeah, the sigma, the capital sigma? That, yeah?
Yes.
Is the variable usually used to represent the individual data values?
X.
X. Represents the number of data values in a sample.
Lowercase n.
N, lowercase n. Represents the number of data values in a population.
Big N.
Big N, good. It's pronounced X bar.
X
It
bar.
denotes the sample mean.
X bar.
Sample mean X bar. Population mean,
Big U. Big.
mu.
Me and you.
Mu, just like the Pokemon, mu. Sigma squared.
O2.
Yeah, this little guy there, the circle with the tail. That's your population variance, population standard deviation. Sigma, right, the little circle with the tail. Sample variance,
S squared.
S squared, and,
S.
yeah, and sample standard deviation, S.
Yep.
All right, now, just a couple more things to talk about. You will, I would say the previous page, so flip back a page, the bottom of that, you're probably going to want to put down the computational model. Let me talk about that first, actually. So the computational model is mathematically equivalent to to the regular theoretical one, the only difference is it's a lot easier to compute. So when you have a lot of numbers, like on the exam, when I just give you like 5 numbers and the mean is a whole number, then I'll make you do that the regular way using your, using your basic calculator. But on the homework, you're going to get stuff with where your mean is a decimal, and you have lots of data, like more than 5, maybe like 8 or 10. It's just a bear to try to calculate that. So, so this computational model is just easier and cleaner to use. I don't like using it in general because it's not intuitive, right? It doesn't, you have to memorize another formula basically. It's not something you can just know. But you will need it for your homework, I believe. There's a couple problems. So here it is, s squared. It's n times the sum of all of your x's squared. So that means, this means square all your x's first, and then add them up, and then sum them. It's the sum of the x's squared. Minus the sum of the x's, so it means add up all the x's first, and then square that. Everybody, you guys see the difference? Divided by n times n minus 1. So this means square all the x's first and then sum them. This means add them all up first and then square that. That one big number. And then the sample standard deviation is just the square root of this. So whatever you get there, you just square root it to get the s. All right, that is it.
Nice.